Today and this week, we're going to talk about organic chemistry. Now, organic chemistry is a huge subject, so we're actually going to dedicate 2 weeks of our course to organic chemistry. Now, this week is going to be dedicated mostly to hydrocarbons, alcohols, and ethers. And next week, we'll talk about a number of other compounds. But the reason why organic chemistry is such a big deal is because, quite frankly, about 90% or more of all the chemical compounds known to man are organic compounds. So these are by definition things that are based on carbon. So organic chemistry really focuses on carbon-based compounds and their chemistry. Organic, of course, means having been alive or from the living. And so we need to understand that these carbon-based compounds, which were something that were once part of that which is alive, such as humans, are very important for us to understand as people in the funeral business. These are the compounds that largely we work with on a day-to-day basis. So, without further ado, there are lots of ways that you can draw out organic compounds. The one on the left, this is a Lewis structure of ethane. Okay, it's a Lewis structure. So that means that we're showing bonds around each of these central atoms. Each carbon is a central atom, and they have 1, 2, 3, 4 bonds around it. That means this atom has 8 electrons around it. The hydrogen has 2 electrons. But that's okay because hydrogen is happy having 2 electrons. Whenever we look at this other carbon on the right, it too has 8 electrons as drawn by those bonds. Remember, each bond has 2 electrons in there. Every hydrogen has 2 electrons. So if this is the Lewis structure of ethane, it gets pretty complex to try to write this. It takes a long time to draw out this Lewis structure. So sometimes organic chemists, and maybe even you, decide that what's easier is to write something called a condensed structure. That condensed structure is what's shown at left. So it takes that Lewis structure and kind of condenses it into something else. So the way this is done is you kind of bag it by carbons. So you see that here we have a CH3 on the left, and on the right we have a CH3, and we could draw it by putting a bond in between, just like what we have right here in the middle between them. Or what we can do is we can eliminate that bond and take the CH3s and get them really, really close to one another. And in doing so, it kind of looks like CH3CH3, which, if we're looking and we're paying attention, is right here. That becomes our condensed structure. And that takes a lot less time to write out than the Lewis structure. Now, this assumes that the carbon that's right here, that C of the CH3 on the left, has 3 hydrogens bound to it and 1 carbon. 4 things. So if we have 4 bonds, then that means we have 8 electrons. So it maintains the Lewis structure as we find it. Now, interestingly, ethane is a really simple structure of a lot of hydrocarbons. Now, hydrocarbons, you'll see here, hydrocarbons are listed right here. Hydrocarbons are compounds that are comprised of hydrogen and carbon, hence the name hydrocarbon. Okay? So, simply, a single carbon that's bound to hydrogens is methane, CH4. Ethane, which is what we just looked at, is C2H6. This is a little bit different. Remember, what we had before, we had a condensed structure of CH3, Well, we can further condense that thing into this, C2H6. But notice that C2H6 doesn't tell you how things are bonded. So I really kind of like this condensed structure that's over here, because this thing actually shows how the structure looks. It shows how things are bonded. The extraordinarily supercondensed structure, also known as your molecular formula, does not show how things look. So you see we have a C6H14 here for hexane. So you see C6 as in hexa, the Greek version of 6, the prefix for 6, has a structure of C6H14. Pentane has C5H12. Pent, as in penta, 5 carbons. So, really, as long as you know your abbreviations from here down, from pentane down, you're good. But these, you kind of have to memorize. Now, the reason why I'm really dwelling on the condensed structure is for this. When looking at pentane, C5H12, what we find is you have several structures that you can draw. You can draw it as a CH3, CH2, 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 CH3. Man, my hand hurts now. I really need to make that a little bit simpler. Let me show you the other tricky trick that you can do to make it super simple. You ready? I don't know if you're ready for this. Are you sitting? Good. Here you go. 1, 2. Wow, I wasn't ready. Doot, 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 doot. Pentane. Now you're wondering, what in the world? Well, it's pretty easy. Every carbon is important. With hydrocarbons, hydrogens are just fillers. Okay? They're just fillers. And so what we find is each of these ends is a carbon. That is the CH3. Notice that what I have is one bond that I'm showing. If this little dot that I'm going to put right there, which you don't need to put a dot there, I'm just showing you as a dot. If that dot is what I'm talking about, that's the CH3. If I'm only showing one bond, then that means I need 3 hydrogens to give it the 8 electrons around it for the Lewis structure, to obey the octet rule. Make sense? And it works the same way on the other side. But if I'm looking right here at this one, that one I'm showing 2 bonds. So let me show you the other bond here. Okay, ready? Shboop. So if that one has 2 bonds, then that means this is a C that has 2 bonds. 4 minus 2 is equal to 2. So that means I have to make that one be a CH2. And what we find is This one shows 2 bonds, and this one also shows 2 bonds. So every angle, every point, every apex, and every end is actually a carbon. The hydrogens are just filler molecules to make sure that you have the right number of bonds to obey the octet rule. So that's C5H12. That's pentane, okay? But I can rearrange it. So what if I take this compound that's right here, okay? And what I'm going to do is I'm going to rearrange it. I'm just going to physically rearrange it. I'm going to change the color a little bit. So I put a C and a C and a C and a C right here in that order. What if I put a C up here? So it's kind of like I'm taking this one and I'm moving this one right there. Okay? So whenever I do that, that means this C that's up here is a CH3 because it's an end. This one's a CH3 because it's an end. This one's a CH3 because it's an end. This carbon is bound to this carbon, and it's bound to this one. So I'll do it like that. So what if I call this a CH? Because now then I got 1, 2, 3 things that are bound to it. This one is bound to that carbon and that carbon, so then that means it becomes a CH2. Or if I draw it in the little zigzag structure that I have, there's this, like that. Well, if we count the structure, if we count the carbons, we have 5 carbons and we have 12 hydrogens. Is this structure right here different than that one? And the answer is yes. These structures are called isomers. So to label something with its molecular formula here of C5H12 doesn't tell you which isomer you have. And as we've talked about before, the structure of a molecule dictates its chemistry. So isomers are no exception to that. So what if I were to take this one right here and I move this carbon right here? So I'm moving it to the next door carbon. Whenever I do that, now then I get something that looks like this, right? A chicken foot. If you like dominoes, here's your compound. It's a chicken foot. When you draw this out, you have a carbon and a carbon and a carbon. You put a carbon up here and a carbon here. So you see 1, 2, 3, 4 right there. This is 1, or 1, 2, 3, excuse me. Are those. The carbon in the middle is, or the carbons that surround are on the outside, have to all be CH3s, don't they? Because they're all on the ends. Just like this one right there. Just like this one right here. So then that means this carbon right here in the middle has 4 bonds each to those CH3s. Is that what I showed in my chicken foot? Yeah. So we have yet another isomer here. 3 isomers just for C5H12. That molecular formula doesn't tell you anything about the overall structure. But you can have that happen with the condensed formulas. So let me show you this. I can condense the formula for pentane up here at the top even farther. I can call it a CH3, CH2, but there's 3 of them in a CH3. Make sense? Likewise, I can condense the structure of the middle isomer, Notice that I have two CH3s that are bound to that CH right here. So what I do is I say CH3 twice, and then comes the CH, and then a CH2, and then a CH3. That's as condensed as it can get. And then if I look at the one at the very bottom, to do this, I have 1, 2, 3, 4 CH3s. So I can just do CH3, and I've got 4 of them in one carbon. So do you see how we're able to condense the... that didn't work very well. Let's get something that's going to be working a little bit better. So what happened? So now then I can condense these structures even farther. And they still show the molecular orientation or the arrangement or the stereochemistry. So what I want you to understand is that this thing called stereochemistry is this 3D arrangement of your atoms. And that becomes a big deal. None of these molecular formulas over here on the right show you that. So what I want you to understand is, for these, they are all what's called straight chain carbons. Look at this. See, it says straight chain hydrocarbons, And so what we find is, as we get bigger and bigger and bigger, so pentane has a boiling point of 36. Hexane has a boiling point of 69. This one is bigger than this one, indicating that it takes more energy to boil it. Does that work with what we know? It surely does. Look at the melting points. For the most part, it takes a little bit more energy to melt something because it's simply bigger. So this is pretty fascinating, isn't it? Alright, so these compounds can be labeled in all sorts of different ways. We can also put them in a ring structure. So before, with propane, I don't know if y'all, I'm going to show my age real quick, but that was a major component of Hank Hill in King of the Hill. He was a propane seller. I sell propane and propane accessories. And so you see, it is CH3, CH2, CH3. That is propane. Well, what if I take this carbon right here and I bind it to that one? Well, when I do that, now then I can go from propane to cyclopropane. Now, propane you can draw like this, right? It's just, kind of the flying V kind of thing. Cyclopropane, how would you draw that? It's just a triangle. Well, I can draw that better. Watch this. Psh, psh, psh. Bing! How about that? That work for you? It works for me. You can also notice that we have these, a bond here and a bond here. So this is like it's a CH2 because we need 2 hydrogens to get the 4 bonds. And it's the same way all the way around. So I want you to notice something. If we were to look at the molecular formula of propane, it's C3H8. Okay? Whereas for cyclopropane, it is C3H6. So starting with the cyclopropane, in this C, n number of C's and 2 times n number of H's. So if the number of carbons is 3, then we've got to have 6 hydrogens, because 2 times 6 is, or 2 times 3 is 6. So this becomes a generic formula molecular formula for cyclic hydrocarbons. What's the difference between this generic formula or the formula for cyclopropane and the formula for just propane? Not a whole lot. If we keep the same standard, we call it CN, so this is in number, so it's like this 3. These things are sama-sama, which is Indonesian for same. Then this is H2N, so, but if it's 3 times 2, right, where this is, N is right there, that's 6, but it has to get a plus 2. So now then, this formula right here becomes the generic formula for just hydrocarbons, right? How cool is that? Now then, we've got a couple of generic formulas that we can use for things. So, how would you draw cyclobutane? Well, how about just a square? Will that work for you? Notice that each of those blue squares is where you would have a CH2. Each CH2 each of those blue squares has 2 bonds attached to it, which means you need 2 hydrogens to attach to them. You seeing a pattern for this? What about cyclopentane? It always helps to make noises. There's cyclopentane. What about cyclohexane? Notice that we have 5 blue squares. What about cyclohexane? There's our 6 blue squares. How fascinating is this, isn't it? Now, remember I said that you can draw these different isomers, right? So one of those that I drew earlier, okay, so let's say we had, I want you to recall this. There's pentane. One of them that we drew, if you'll recall, looked like this. So what we find is this carbon right here, this one right here, is a CH3. But the longest chain is right here. And so in terms of trying to name these things, when you have these substituents, these alkyl groups hanging off the end, okay, so we'll make it this thing. This right here is this alkyl group, right? Because it's a CH3, we call it a methyl. Now, what's interesting about this is we can use this to begin to name things. So, for instance, you use the green highlighted stuff to get your parent. So, for naming, you find you're going to name the parent, okay? So it'd be like my parent name for just me would be Cabot. And then you name your substituents. So then you name your alkyl groups. And then you've got to number your alkyl groups. Okay? So let's see how this works real quick. It's real simple naming. Number 1, name your parent. Number 2, name the alkyl groups. Number 3, number the alkyl groups. So I like to do it like this. The big green highlighted thing is a 4-carbon chain, right? So a 4-carbon chain from the previous slide is butane. Okay. Ane indicates it's a simple hydrocarbon called an alkane. Alkane says that you've got all single bonds. This is what all the single ladies like. Now, with butane, it's not just, you can't just call it butane because you've got that blue methyl group hanging off. So you call this a methyl. But it kind of looks weird to have a methyl on one side and a butane on the other. So what you do is you take this methyl group and you go and you tack it onto the butane. So we could call it methyl butane, but it doesn't tell us much. And there's a reason behind that. Because what you've got to do now is you've got to number. You could number where you go 1, 2, 3, 4. You now number your parent, okay? So you number your parent. All right. Well, we could do it that way, or we could number it the other way. 1, 2, 3, 4. Depends on how you read. Do you read left to right, or do you read right to left? With organic compounds, it don't matter. You read either way that's bestest. And so in this case, what you're trying to do is you're trying to get to a number here. You want the lowest number. Okay? So this is going to be where you're trying to get this number right here. That needs to be the smallest number. And the smallest number is this red 2 right there, isn't it? So then what you do is you put a 2 and a dash in methylbutane. So the name of this compound now is 2-methylbutane. That's different than labeling something as pentane. And now then we have a systematic way of naming these things. Okay? It's a lot better than hopping online and finding the top 100 names of 2020. So, we can name these in all sorts of ways. So ethane, so we were just looking at, if I have methane, if it's a substituent, then it becomes methyl. So notice you take the methane, you drop the ane, and you add YL. So it becomes methyl. How are you going to do that for ethane? It becomes ethyl. How are you going to do that for propane? It becomes propyl. Or, it doesn't have to have a bond on the very end. It could have the bond in the middle. And in that case, you call it isopropyl. So isopropyl alcohol kind of has this structure. Isopropyl alcohol is also known as rubbing alcohol. It's a great disinfectant. Now, how would I name this thing? Well, notice that I've gone ahead and numbered all those, numbered the parent for you. 1, 2, 3, 4, 5, 6. Now remember, I could number it as 1, 2, 3, 4, 5, 6. Okay, either way. But either direction, I have 6 different carbons in that longest chain. The longest chain is your parent, because your parent tends to be biggest, especially when you're a kid. So what we find is this is a hexane. Ane because everything's single bonded, right? So it's an alkane. Now, we need to figure out what to do with this thing, because we haven't numbered it, we haven't labeled it, it doesn't have something yet. What is that? Oh, that's right. This is a methane, right? Except it's not a methane because it's not CH4, It's a meth, drop the ane and add YL, methyl. And now then, this methyl needs to come on over here and get attached to the hexane. So we could call it methylhexane, but the problem there is that methyl group could be on number 2 or number 3 or number 4. Which one's it going to be on? So we have to number where that methyl group shows up. So is it going to be number 5 or is it going to be number 2? And the answer is, remember, it's the lowest one. So that becomes 2-methylhexane. Make sense? Excellent. You'll get a chance to do lots of practice here. Let's see if we can name these. This is a little different. Notice that we have the supercondensed form over here. And we have the Lewis dot. Well, it's kind of a Lewis structure, but kind of not. It's a semi-condensed on the left-hand side. So we're going to work from the left-hand side, okay? We're going to be simple like that. So how this going to work? Because my English is not so good, eh? So if I number this thing, I can number it as 1, 2, 3, 4, 5. Or I can number it backwards, 1, 2, 3, 4, 5. It doesn't really matter, right? Either way. So I have 5 carbons in that longest chain, right? So that becomes a pentane. A pentane. But now then I've got to figure out what to do with this thing and with this thing, right? Because I haven't done anything with them. So this one's a methyl. And this one here is a methyl. So what should I do? Should I take this thing as I've done before and do that? And then I can take this one and do that. This looks kind of weird, doesn't it? Do we want to label this thing as methylpentane? Or is there a way that we could label it better? So if I have these 2 methyls, what if I take these 2 methyl groups right here and I say, well, I need to put a methyl there because I know that there's a methyl, but instead of saying methyl, what if I called it dimethyl? Because remember, before we talked about how di means 2. So dimethyl means I've got 2 methyls. But where are those methyl groups? Well, one of them, this methyl group is on number 2, right? Because if I'm looking at these things right here, I have to go with the smallest number, which is that number 2. Okay? So, but what about this other methyl group? This one is a 2-methyl as well. So, how do I do this? I could have called it a 2-methyl pentane. That sounds weird, and I already said dimethyl sounds better, right? It's more condensed, it's a little bit simpler. So, could I just put a 2-dimethyl pentane? No, because look how many I got. I've got this one, and I've got this one. I've got 2 2s. So then it becomes 2-2-dimethyl pentane. Then this becomes our actual structure, our name for this species. So that di is an important thing, and you've got to put the 2 numbers there. Otherwise, you don't have the full name there. See the importance of trying to name the hanging off things, those alkyl groups, those substituents? That's really, really important. Naming those will help out. Well, what if I've got something a little bit different? What if I've got this? Now, this looks weird. Okay, I will admit it kind of looks weird, but I want you to focus on something real quick. Looky here. I've got a chlorine bound to a carbon that has a double bond to carbon and single bonded to a chlorine. Let's see if we can simplify this. So there's the carbons. Here's a chlorine here. Here's a chlorine here. How would I do that double bond? Oh, right. Boop. So there's the double bond. Okay, so now then that looks a little bit simpler. If I'm looking at this particular species right here, I know that chlorine is closer to fluorine than carbon is. So that means that I've got a little bit of a dipole. So I'm pulling this way and I'm pulling this way, right? Which means I've got a net dipole like this. Kind of averages, kind of pulls things along. So this is a polar molecule. Interesting stuff. So you can start to see this drawing on the far right. This drawing is what's called an electrostatic map. An electrostatic map kind of shows you a pictorial way of looking at polarity. Instead of just doing the dipoles, notice that these are just the simple dipole showing the positive end in the arrow, to putting an electrostatic map that shows it a little bit better. So now then you can see that down here, this is very much delta positive. And up at the top, it's very much delta minus. And so you can start to see that dipole play out, can't you? So that's 1,2-dichloroethene. Notice here, okay, this is a weird thing, so you just go ahead and do this. This is a 2-carbon chain, right? So a 2-carbon chain is an ethane, but it is not an alkene. It's not an alkane. Alkanes, these things are single bonds, right? Alkenes, E-N-E, is double bonded. So you got a double bond, okay? So it's not an ethane, as in an alkane. It is an alkene, so it becomes ethene. Now then, you also have 2 chlorines, don't you? So you could label it as, because these are your substituents, right? Those are your groups that are hanging off. A dichlorine, ethene, but that sounds a bit awkward, doesn't it? So what you do is you drop the I-N-E, the ending, and you make it into an O. So it becomes dichloroethene, but you have to label it as in which carbon it belongs to. Because remember, just saying dimethyl pentane doesn't tell you where those methyl groups are. Likewise, saying dichloroethene doesn't tell you where the chlorine groups are. And if we look here, it's on the number 1 and the number 2 carbon. So we would call it a 1,2-dichloroethene. And what I want you to see here is these things are north of the alkene. Both of them are north of the alkene. So now then, this cis right here, that cis basically is not dealing with my sister. It is saying this is the label if both substituents, I'm going to spell this out for you, substituents, that means the hanging off groups, those are those groups, if both substituents are either north or south of the alkene. Okay? So that's kind of an important thing. This is the label that you use if your substituents are either north or south. Both. Both of them have to be north or both of them have to be south. that means we're going to get a nice little polarity map that's shown right here, this electrostatic map. We can also look at something different. What if we're looking at something that looks like this? So there's this. It's an alkene. I put a chlorine up top. I put a chlorine down bottom, like this. When you have this thing right here, now then, we see that we've got a polarity this way, and we've got a polarity this way, don't we? The dipoles are in opposite direction, aren't they? So that means they cancel each other. But you can still see on this electrostatic map that we have a delta minus up here and a delta minus down here, and you got the delta pluses that are kind of hanging out in between, right? Just like we showed. But I want you to notice something. This is also an ethene, and it is a 1,2 dichloroethene. Here's number 1, here's number 2. Or you could reverse it and say number 1 on the right and number 2 on the left. But notice those chlorines are on opposite sides. So that means this has to be trans. So what does that trans mean? Well, that is the label if your substituents are not either north or south, but they are, one's north and one's south of the alkene. Notice, this thing is north of the alkene, this thing is south of the alkene. So it's north and south of the alkene. Trans, this trans means opposite. Opposite. And so now then, we can start to see that even these names can start to distinguish compounds one from another. Are you starting to see how complicated organic chemistry is and why we have so many organic chemicals in the world? Because life is complicated. We haven't figured out why a bunch of carbon and hydrogen and oxygen and nitrogen and sulfur and phosphorus and lots of different salts can come together and provide consciousness. We can't explain that. We can't explain why, when that stuff still being together, but without blood pumping and oxygen going, there is no consciousness. We can't figure that out. So, there's also some trivial names that are there as well. These trivial names are sometimes called common names. Now, the reason why I point this out is because there's a lot of common names that are used in the funeral business. Okay? There's a lot of these common names that are used in the funeral business. Not necessarily for alkenes, but for other species. So you got to be paying attention to some of these common names. I'm not going to make you have to memorize all of these. You'll be okay not having to memorize these trivial names or these common names, but you can start to see how things play out. Notice that we always number from the end closest to the alkene. The alkene is kind of your group that you got to reference. That's the head, if you will. So then this would be a 1-butene on the far right, or a 2-butene on the bottom left. And we can name these things all different ways, because you have to name them relative to the alkene, alkene gets preference, so it gets to the lowest number. So now then, we have a different rule. Yes, you got to look for the longest continuous carbon chain, which is right there. Okay? Yes, you have to look for the substituent here. But the substituent, that CH3, and sometimes it really does help to draw out how it looks. So that would be how it would look. So notice that the longest carbon chain is right here, and that here's our substituent. Okay? I like drawing that skeletal structure better. That's what this is called. Sometimes it's called line bond. Sometimes it's called skeletal. Skeletal structure. Sometimes that's helpful. So then, notice that the two big substituents are both north of the alkene. If we look at the other side, we have one north and one south. So the one on the right-hand side is labeled trans, the one on the left-hand side is labeled cis. You can also have alkenes that are, in fact, cyclic. So when looking at this, cyclopentene is shown at left, and we can draw the line bond structure in the left center. We can also have cyclohexene, and you see that structure play out as well. All right, so now then, we don't just have to have alkanes and alkenes. So remember, an alkane is all singles, right? An alkene has one or more doubles, okay? An alkyne has a triple, and that's where I'm talking in this slide. So you can have ethyne, also known as acetylene, as in acetylene torches. Notice that it's a 2-carbon chain, ethyne. A 3-carbon chain would be propyne. So you see what you did? You took that propane, but you get rid of the ane and you put yne for the alkyne. Then you can have butine, 1-butine, or you can label it as 2-butine. Depends on where your alkyne is. Notice that here on the left, we have it at the number 1 and 2 carbon. When we look at the center right here, labeling it the same way, it's at the 2 and the 3. Notice that we don't label it as a 2,3, we just label it for the first carbon that is attached to the alkyne. It's assumed that it follows to the next carbon. That gonna make sense? I hope it does. Now, just like with ozone, you'll recall with ozone, I want you to remember this, that you can have an oxygen here that has a double bond to this oxygen to a single bond there. Or it can have a resonance structure where you have an oxygen single bonded to this oxygen, which is double bonded to this one. So this is that resonance that can occur. You can do the same thing with certain organic compounds. So here's one example of that. This is called benzene. Benzene's quite toxic, so you probably won't mess with it very much, but I want you to notice this. With benzene, I have a double bond here, and a double bond here, and a double bond here. And in between, I've got single bonds, okay? So now then, let me redraw that to show you the single bonds in green, okay? If I look at the structure to the right, the single bonds have moved. They're in a different spot, and the double bonds have moved. But if I look at that, it's still, if we're looking, double, single, double, single, double, single, right? Double, single, double, single, double, single. As a result, these things are also resonance structures. Okay? So now then, because these are resonance structures, because benzene has resonance, there's something interesting we can do. If I draw the skeletal structure, that would be the skeletal structure for the one at left. I can show it doing resonance to form the skeletal structure for the one at right. See, we'll do it this way because it makes me happier this way. Makes it look like I can draw well, right? Y'all can pretend with me. You see this? Can you see the double bonds shifting a lot easier, drawing that skeletal structure? So now then, what we can do is we can take this thing, and we can take this thing, and we can draw it in an interesting way. And the way we do that is we say, well, here's my, oh, that's terrible, as my 3-year-old son would say. That's besser, as Germans would say. And what we do is we put a big circle in the middle. So what this does is it shows this right here. That is now what we call our resonance hybrid. So when you go watch CSI, you'll see some of these drawings in the background where you have the resonance hybrid for benzene back there. I'll draw it better. How about that? There we go. There's our resonance hybrid for benzene. A circle in the side of a hexagon. So resonance can occur in organic chemistry as well. And when we look at that, we start to see that the electrostatic map shows a lot of electron density around the center of the benzene and a lot less electron density around the outside. Notice that this is a lot of delta minus in the middle, right? All the But on the outside, we have a lot of delta pluses, don't we? So what this does is it says that we can actually do a lot of different things. Benzene can solubilize lots of stuff. All right. So this is toluene. So you see the benzene? And then look, right here, I have a methyl group hanging around. So that CH3 that's right there is toluene. Now, why do I point out toluene? Toluene is a solvent that's used in a lot of paints. It's also used to dissolve a lot of different organics. Pretty fascinating. All right, There are organic halides that are around. I already introduced you to this. Remember the dichloroethene? Well, how about we say chloromethane? Notice that what we have here is we've got a dipole. Do you see the dipole in the electrostatic map? And you have the same kind of thing with dichloromethane. We have a net dipole that's this direction. And what about trichloromethane? Well, trichloromethane is also known as chloroform, and it has a large dipole moment as well. Well, for carbon tetrachloride or tetrachloromethane, I want you to notice something. That dipole is a four-way tug of war where no one wins. So there is no dipole. None whatsoever. So that becomes kind of interesting. All these things for these different chlorinated deals. Remember, these are called halides. So halides means fluorine and chlorine and bromine and iodine, or iodine, as we say in the U.S. You can have different structures in terms of your benzenes as well. So DDT is shown at the bottom. Lots of chlorine there. It's really great at helping us not have bugs. Problem is, it's really great at being an endocrine disruptor. Oy, that's frustrating. So this benzene that we see right here at the left, with a bromine and a chlorine, the way you would name that is you would call it a benzene because that's the longest carbon chain. That's the parent, right? And then you have a bromobenzene, and you have a CH-chlorobenzene. But which one's number one? Well, this time, if you have things where you got to figure out what the number is, you number the smallest number goes with the biggest atomic number. Bromine has a bigger atomic number, so it becomes 1 bromo. Chlorine becomes 2 chloro. So then you would end up naming this thing 1 bromo, 2 chloro benzene. I won't make you name something so complicated as DDT. I just wanted to show you that structure. Alcohols kind of look like water, but instead of an H on the end, we have a hydrocarbon on the end, or a benzene. So ethanol you see in the middle, that is a great disinfectant, right? It's also drinking alcohol. Phenol is another disinfectant. Phenol, which you see here at right, with the benzene with an OH group, which is your alcohol, and alcohol by definition has some little random organic thing and an OH on it at some point in time. Somewhere on that structure there is an OH. Phenol smells like Band-Aids is another disinfectant. So both of these things, being disinfectants, tend to be pretty helpful in the biz, as y'all would say. And because you have the OHs, then that means things that are soluble in water sometimes are relatively soluble in alcohols. So there are different types of alcohols. If I have one, okay, so you gotta look at this. This carbon right here is our reference carbon. So this primary basically says I have one R group, one random group on my reference carbon. Okay? If it's secondary, that means I have 2 R groups on my reference carbon. And if it's 3, I would have 3 R groups on my reference carbon. This plays a pretty significant role. So for instance, a primary alcohol would be something that looks like this. This would be what we call propanol, because it's propane with an OH. This all is here. You do have to show the H's with your OH. You can only assume H's that are bound to carbon. So that's propanol. If I used the isomer, if I looked at the isomer for propanol, there's only one, and it looks like this. So there's the propane, you see that? But if I put the OH here in the middle, now then that becomes isopropanol. And if I'm looking at this reference carbon right here, that's secondary, because I have 2 R groups on that reference carbon. Whereas for propanol, I have 1 R group on that reference carbon. So that means it's primary. Okay? You can have a tertiary alcohol, but you got to go something that's a little bit more complicated than just propanol. You have to go to a chicken foot with an OH. So how many carbons do I have? It's got 4 carbons, right? So that's a butanol. So this would be called T-butanol, because if you look at it from an old school way of doing this thing, you could draw it like this. So you would call this T as in tertiary butanol, because you have 4 carbons. Notice that my reference carbon here is tertiary, because I have 1, 2, 3 substituents. Alright, here's some other common alcohols. Wood alcohol is methanol, over here at the left. I showed you propanol and isopropanol. Another one is this T-pentyl alcohol at the far right. Some of these things that are pretty important is methanol, when consumed by living organisms, produces formaldehyde. There was an episode of House that had that. Now, the reason why some of these alcohols are pretty important is because we get something that looks like this. We have glycerin, also known as glycerol, on the far right-hand side. Those are some common names that you probably want to pay attention to. As you do this propylene glycol, you see these a lot in some of the cosmetic products that we use. It's a moisturizer, this glycerol, so it'll make skin look, instead of nice and dry, it'll help to moisturize the skin. And sometimes you even use this in terms of your funeral directing and embalming to make skin look more moist, because that's a typical problem with a lot of bodies. We find that these bodies lose moisture very quickly through the skin. So to keep that from happening, you can apply glycerol to help minimize the moisture loss and to maintain that pliability and natural look. Alright, so with these alcohols, you have a polar end and you have a non-polar end. Notice that the hydrocarbon is the non-polar end, whereas the alcohol is the polar end. So alcohols are really handy because they can often dissolve both polar and non-polar things, compounds. And that's really quite handy in a lot of situations. And finally, I want to talk about ethers. Ethers are really amazing because now then, instead of having that OH there, what we do is we have an R group that's bound to an oxygen that's bound to another R group. So these ethers are less polar than alcohols, but sometimes these ethers are pretty handy. So there's a compound that we'll talk about later on that is methyl salicylate, if I recall correctly. And methyl salicylate, also known as oil of wintergreen, which is used in to put underneath the nose for a body that is advanced in decomposition. Helps you control your urge to vomit. That methyl salicylate is actually an ether, and we'll talk about that later on. So these become pretty important for you as well. Methyl salicylate is one of those type of compounds that you need to memorize for the board. So, thus concludes our organic chemistry part 1. Remember that whenever you're looking at some of these things, some of these compounds, to find what's most simple. So in the case of this one here, we have a simple ether in the middle that we're able to work with. We know it's an ether. And now then, we can draw our nice little ether bunny just for you. Have a great day.